you just want that down?
Oh. Here?
Yes.
Okay.
Yeah.
Hello.
Hello.
Okay. Ready to start? Okay.
Yes.
Thank you, everyone, for coming here and joining us. Thanks, everyone that is joining online. As always, we like to start our meetings with acknowledging the traditional custodians of the land from which we meet, work, and study, and pay our respects to their elders, past, present, and emerging. I would like to welcome today Hongfang Liu. She is an amazing guest that we have today, and we want to thank Wendy for making all the contacts and arrangements. And I know that you've known each other for a long, long time, so that's one of the benefits of networking throughout our careers. And she's the Bradley McWilliams Chair Professor at the McWilliams School of Biomedical Informatics and serves as a Vice President of Learning Health Systems at UTHealth Houston. I'm going to read this because there's a lot here. She's directing the Center for Translational AI Excellence and Applications in Medicine, which is the cool acronym, Team AI. I think that puts her in the right place to continue these discussions about clinical AI and the art of possible, which have been sort of like the thread that has connected all the different sessions that we've been working on. Her research has been recognized through several awards, including the NSF Career Award for Biomedical Text Mining, the NCATS Innovation Award for Open Health Natural Language Processing, the AMIA Donald Lindbergh Award in Informatics Innovation for Context-Aware Artificial Intelligence, and the CPRIT Established Investigator Recruitment Award. Her current research focus is to advance translational science and bring novel data science, informatics, and AI solutions to empower real-world data-driven research. So we're honored to have you here today, and we look forward to listening to this presentation and learning from your trajectory and what's coming in the future. So please, a bit of an applause to welcome
Thank you very much for a nice introduction. So I'm going to share screen. Just a second. Can you all see the screen well?
Yes.
Okay, great. So basically, I'm currently, as you see, I'm in the UTHealth Houston, but I have a disclaimer. So I moved from Mayo Clinic in Minnesota to UTHealth Houston, and those are two distinct organizations. And those happened last year. So some of the materials I present here, actually the work done at the Mayo Clinic. But the perspective and how to think about moving forward, some of the view is coming from my new environment. Just to get, I believe many of you know Mayo Clinic, which is currently be branded as one and only. So it has been ranked top across the U.S. here, as well as the world as the top one hospital. But in the Texas Medical Center, it's being labeled as the world's most comprehensive life science ecosystem, which we'll get a little bit into it with a couple of slides. So my current organization is in the medical informatics or American medical informatics perspective in the US. This is a figure we always want to brag about it, say where we are, why the McWilliams School is the only standalone school dedicated to biomedical informatics, medical informatics. In the United States, we currently have over 100 EMEA academic forum members. and all the others are in the form of, division, department. None of those are actually appear as a school, so we are the only freestanding school. It's the largest in the nation. And for those who not be able to visit Texas, United States, this is the Texas Medical Center. When you think about it, you don't really know how dense it is. So this will give you some idea. In 2 square miles, we have about 56 institutes here. You may heard Rice University. You may heard MD Anderson Cancer Center. And so we are actually located across 50 minutes walk across each other, which is a wonderful environment. I put those 2 constructs, the Mayo Clinic, Minnesota and Texas in a reflection, because I basically say Mayo Clinic itself is the #1, but Texas Medical Center is real world, means that this is actually how the real world looks like. So that's the kind of the thinking I currently have regarding that. So this is the outline of the following talk. So I basically first will discuss healthcare in the digital era. Many of you probably already very knowing this. Touch upon the work we did related to healthcare AI prior to generative AI. Then touch upon the Open Health LP consortium. Discuss barriers to translation and thoughts in the generative AI era. And lastly, I conclude with something I'm championing, say, how do we move forward in the translational science related to AI? Dive into it. In the United States, we generally have this called clinical translational science from the National Institute of Health. So we have the CTSA award. So this is try to summarize how clinical translational science look, which is from basic science research to human clinical research, health service research, and the population, social and policy research. But if you look in the digital era, healthcare AI, this has been fundamentally changed since in the last 20 years, where we have the effort of precision medicine, which is learning from the high throughput technology side of the biotech side to allow us to do rapid evidence generation. Then we have learning health system, which is focusing on how do we translate practice generated data to influence to come up with evidence for healthcare system optimization. This is the most recent ones that due to the digital transformation, we now have ability to do telemedicine and leveraging wearable device to measure patient outcome and fundamentally allow us to have a AI-empowered digital health potential. Want to little bit emphasize that digital health has been around for a while, but not truly have a wide dissemination. But due to COVID-19, this becomes something really, really changing how we see healthcare of the tomorrow will look like. Learning health system for this audience may not need to deep dive, and those are the general concepts, is that if you have the data to be digitalized, computational accessible for any health problem or interest, we should be able to use that data to generate evidence and translate that evidence to applications and disseminate and adopting, so we can change, learn how to practice medicine and do healthcare delivery. But the meanwhile, I want to say learning health system in itself is not a new concepts if you truly think about it. When we practice evidence-based medicine, we also take a learning perspective to look at it, where we have the basic information, expert opinion, put the case reports, and those are the data point. But those data become through traditional clinical translational research become evidence. Then that evidence become clinical implementation into clinical practice. So not really new. And then when you compare evidence medicine to healthcare AI, if we follow the data information, knowledge, wisdom pyramid, that's generally we, as an informatician, look at the whole thing, is that we want to generate from the case reports to guideline. But the process is that we go through the rigor process of getting evidence. Healthcare AI itself right now formulated as from past, how do we predict the future? And this is based on current data. How do we deliver application? And there's something hidden there. This is something we have been thinking, how do we really look at this problem? So to me, the major difference from the traditional evidence-based medicine to the current healthcare AI-related empowered medicine practice is that one is expert-based, the other is more data-driven. One is human-centric, basically the expert review and synthesize, conducting experiments to do that. The other is just directly use the past to inform the future. Basically leveraging the data, connecting historically, try to think how do we move the data into wisdom application to deliver. So in the past 20 years, this right side has been my research focus because I always want to leverage the data and build application on top of the data. So this comes to the work we've been working on, and I have something special about my role in Mayo Clinic for 12 years, which is my primary institution. I was their first PhD computer scientist as a consultant. So basically, I feel I have a lot of responsibility to push to make data to be able to generate application on top of the data. So due to that special kind of position I had, I was, in 12 years focusing on how do we build a learning health system, establish a data infrastructure and analytics pipeline to support the learning health system. And it is not, rocket science when you truly think about creating a data platform and building analytics platform on top of it and working with clinicians and try to say, you actually can use the data here to help you to acquire knowledge for point of care delivery. And so been working on this in multiple fronts. Generally, we, I have a team about over around 20, 30 people, depending on the time frame. So we either do methodology advancement related to, data quality check, how to do natural language processing on the data, transform the clinical narratives into structured data. We also do a lot of things related to infrastructure development. Back then, I've been labeled as advanced IT because I work with our IT team to set up the infrastructure and work with our, research group there to set up a consultation service. Of course, it's not an easy task as the only computer scientist there to be as a leader there. So it needed to say, how do we use computer technology to do health service research, to do epidemiology research, to do those type of things. A lot of work along that. And then we have workforce development, all those different activities. We even set up the master degree in healthcare AI the last 2 years when I was there. So those, on the research side, basically those was anything we do there, we've been kind of try to bring two different perspectives. One, as a researcher, how do we solve this problem? The other is that how do we actually implement to have real world impact? Those are the piece which is around translational. So one thing we achieve is try to, it's actually develop a clinical phenotyping for learning health system in silico and build a software stack on top of the data platform, allow people to interact with the clinical data there and to derive clinical phenotyping. So the local data warehouse and the local data is here, but through tooling, we'll be able to support many different use cases leveraging the data. And when in the following, I just highlight some of the examples. This is a very simple example for me as a technology person, but for the clinical side, it's a significant problem. This one is related to how do we make sure those pediatric asthma patients to get the care they need? How do we support the pediatricians to support their point of care decision-making? One simple task was doing is that how can you perform automated chart review and tell me the current status of those patients? First, who are those patients? Secondly, what's their asthma management currently look like? Do they have, well managed, or is, have exhibition, and how many, ED visits they have, those type of things. So this being a translational effort with multiple, National Institute of Health grants to support the activity. Technology side is simple. It's a rule-based NLP system, but the application side is have many different applications related to, clinical research, related to trial recruitment, and also related to clinical decision support. And in one of the project, we even try to assess how residents do clinical documentation regarding pediatric asthma. Do they follow guideline-based practice? And this become, point of care clinical decision support system. We call precision asthma care through asthma guide precision system. Very, very simple from the technology side, as I keep mentioning. But the clinical impact, if you work with the clinicians, with the clinical researchers, they can change that into a wonder, which, talk about it in a way which you couldn't imagine. And this being also don't know the current status, but this before I left, this was thinking to be put as an app into the Epic to deliver the pediatric asthma care. That's one example. Second example, I want to show, besides chronic disease management side of the application, we also can leverage in natural language processing for the AI technology, the data to allow real-time adverse events surveillance and risk prediction. This is also a funded project. all those projects become possible because we establish a real-time, near real-time data platform with analytics capability, which allow the the EHR data to be able to use in the near real time. This specific project basically come to people want to extract, identify patients who have post-surgical complications. And then we suddenly think is that identify them is not enough. We should try to do prediction and handle the risk. So this is a case of, how do we do AI-empowered healthcare? Specifically, as an AI person, we are so fortunate with this quality improvement project in the nation called National Surgical Quality Improvement Program. The reason why we like it so much because they have the patient charts manually reviewed. And that manual review give us training data for building modeling prediction algorithms. And long story short, this is just over the years, we demonstrating we needed to get information. We needed to get the information from the text because when you have keywords to be extracted from the notes, you have better detection of the clinical important outcome, colorectal surgical site infections. The red line indicating we use the Bayesian network compared to logistic regression. But this table just showing you, as soon as you use the keywords from the clinical documents, it's AUC 280. But if you're adding risk factor together with that, it'll get 82. And then when you think about clinical important colorectal surgery and some of the false positive we identified, clinician review it and judge to be also clinical important. So if you factor that in, and we can achieve AUC for detecting surgical site infection at 90% accuracy, AUC. And we do more as related to that is that to do real-time risk prediction. This is leveraging the AI deep learning models for real-time individual risk assessment, some of the articles here. Besides this one, then you can also do observational study and for trial accrual. This is another study was doing, stroke prevention of silent infection, how to develop algorithms to get, silent brain infection to be extracted. Objective is that silent brain infection itself is not a coded concept in the US. So there is no ICD-10 codes about silent brain infection. And also white matter disease, those are not there. But for ICD-11, there is a code for silent brain infection. And the goal of this is that can we detect those patients with silent brain infection? And can we see for those with silent brain infection, do we need to have preventive therapy for them to prevent the risk of a future stroke or dementia? On the neuroscience, neurology practice side, actually it is not clear if we should have the preventive therapy as a part of the clinical prevention guideline. There's no such a thing say if you have silent brain infection, provide preventive cardiovascular related therapies. So objective, we did this from the neural imaging reports to identify those patients, straightforward, and just through the rigor process, we get those cohort to be assembled. And after the cohort to be assembled, you can do a lot of things. This one is the generated real world evidence about the risk associated with those patients with silent brain infection. Sorry for the picture, but this is just showing you the real world data has power. The data used for generate those real world evidence actually coming from Kaiser Permanente. We didn't use Mayo Clinic's data because they are not their destination medical center. They don't have the primary cohort and the longitudinal follow up as we would like to have for this kind of study, which is you do want to have good coverage of the the data elements. So I move on. So those are just showing you prior to the AI become very hot. In the last 15 years, we've been working on building AI system for healthcare. And so that's in one institution. Then natural things people will ask is that how do we move beyond one institution? So for this project, I need to mention this consortium called Open Health Natural Language Consortium. This was initiated back in 2009 by Mayo Clinic and IBM to move beyond the EHR to deliver knowledge at the point of care. So of course, the problem they are trying to solve is that how do we transform the clinical text into something which we can use for all other data analysis. So in Mayo side, they release CDTH, and in IBM side, they release a system called IBM MedCat. So IBM MedCat become IBM Oncology, and the Watson Oncology. In Mayo side, is a transition to Apache CDTH through the ONC Sharp-N project, which is a big $50 million funded to support the secondary use of EHR. And Wendy back then was also part of this team related to how do we move the Mayo CDTH to Apache CDTH. So that's the summary of this project. Basically, it's a strategic health IT advanced research projects from 2010 to 2014. Chris Xu was the PI and from Mayo Clinic and developed tools and resources to facilitating the use of that. So in 2010, 2013, as I'm leading this Sharp-N data normalization, we develop algorithms and also resources to facilitating the data standardization, normalization of EHR data. So we can use EHR data in data analysis. So the diagram, just say, the achievement of this is that they'll be able to standardize both structured data and unstructured data into a common format. After you have the common format, you can do a lot of things on top of it. In 2013, those are the, at the end of the Sharp-N project, we got many different projects going with CDTH, Apache CDTH, but we have a lot of innovation components which are not mature to the level to be put into Apache CDTH, become standalone tools around. And this is basically the in 2013. So in 2014, 2017, I've been able to move forward the project with leveraging the technology to support clinical and translational research through these grants. And that basically trying to say, can we standardize the data capture? Can we bring the tool to the end users? Can we make the community to adopt that? And from 2017 to 2023, we got this effort, which is the multi-site collaboration. First with 4 aims to be proposed, which is trying to say, okay, you got NLP artifacts. How do we, improve the algorithm development? How to generate synthetic data for training purpose? How to make use of that data in a privacy-preserving computational approach? How do we, partner with different community for translational science excellence? So those are the history of the OHNLP consortium. But in 2023, this is the current status, which is basically we set up the infrastructure for community to deploy NLP systems, infrastructure. We supporting the translational researchers to use EHR data, supporting them. How do we use text data? We have a lot of tools to supporting it. And this is the key components, which I will illustrate more at the end, which is Hope, Science, Trust. So I still just touch upon hope basically means that we don't try to invent a problem to solve. We should work with the team, domain experts, try to see what kind of issues they are facing, and we want technology to bring that hope. We also need the technology to be in a adopting the science approach. Basically, needed to have evidence. Lastly, we needed to build a trust. Don't give me a system or algorithm or methods which have no real world translation capability, and also ensure the stakeholders trust the technology. So those are the community we've been promoting this, and then in 2024, many people started to wondering, do we still need NLP, natural language processing, with the technology? This basically in the era of large language model and in NLP, and the current thoughts of us is how do we leverage large language model, generative AI technology, to help us with the NLP development. So OHNLP, I mean, on the method, on the innovation side, we did a lot. However, we face those what we call model reproducibility, and just go through quickly. Despite the promising results, we actually, after we try to do this on the national level, we face critical situations, which is reproducibility. So in the context of secondary use of EHR, we know a lot of data was generated from the real world, and there's heterogeneity regarding how the EHR to be connected, what kind of EHR be adopted, what kind of data connection there, how the data to be used, what are the data to be reporting. So there's a significant reproducibility challenge and a significant downstream implication. And the famous example come from University of Michigan regarding the sepsis algorithm from a very famous, EHR system called EPIC, which is they have a sepsis algorithm which they want hospital to deploy. There are many hospitals, their EHR system actually have the sepsis prediction model. The Michigan team actually did the evaluation, which showed that the observed model performance is 63% AUC, but the internal documentation show about 76 to 83 performance. For people who work in the field for a while, this is no surprise because we know that the general model and the hospital optimized model, you definitely have a difference, and we don't know how the epic sepsis model being generated. So there's lack of open transparency regarding that. So our question is that, AI is cool. Everybody want to go to AI. Not many people want to do the data work. Data is essential. So in the, human computing HCI community, this being called as the challenge of data cascading. It's the downstreaming effects of the data issue results into because of the technical debt over time, and emphasize the important how to make sure the data to be correct and work properly prior to do any modeling. And when we work on a single institution, we were so happy with that performance, that achievement. As soon as we go to multi-site national level, we saw so dramatic a difference. The standards interoperability, when I work at Mayo, the standardization is a key. They have data governance group standards, stewardship. Everything was standardized. Right now, at my current institution, there's no standards adopted. There's no standardized implementation. And even for the practice level, there are many built-in functions, but this is varied across different providers. The data documentation, connection, extraction, when we build models, how those things be used, those are not captured. So then this is causing the data to be very hard to use. Yes? So we did some analysis regarding the variations, and this is just showing you 3 different institutions, how they look different regarding how they document information. So, 3 different institutions, you see their distribution quite different. Many factors regarding how these things should be done. It's so challenging. That's the reason why it's so expensive. And then also when you come to multi-site institution implementation, we face, most institutions, not all the institutions have expertise. Not all the institutions have policy in place for the people to use. And not all the institutions have the infrastructure in place, and also not all the institutions have data to be in the perfect way to be used. Some are scanned documents, some are stored in a server somewhere. So those are the challenges we're facing during the implementation. And this is the experience we had on the open house NLP side, as well as our local, compared to what we did locally. And when you go to multi-institution, what's the struggle we see? To really see this as the evidence, we did a scope review. Say, this only happened to me as a OHLP, which tried to get all the other sites to adopt. And we did a systematic, did a scope review and follow some systematic review approach, which is trying to see over the years, how many of the NLP solutions be used to address clinical questions, and what kind of things they're being reported. So the data source of this scope review is that from 2009 to 2021, observational studies focused on use of the NLP solution to address clinical questions, and the process is that, follow the process. And to our surprise, at the end, we only have about 50 studies using NLP to derive features for observational study. And we distinguish two different studies. We view those used for NLP algorithm development, machine learning, model development. Those are measurement study where they reporting performance. But when we say the utility of those systems, those are generally come to clinical research, which is observational study. Those are the things we distinguish them. This is a full figure showing you that this is from the PubMed simple search, give you that, which is what's the difference between EHR-based observational study and the EHR-based observational study utilize natural language processing, which basically means they use notes. And so we see those using the text data there is in less than 100. But if you see how many articles using EHR, many. And for those who are working in the clinical domain familiar with EHR, we know majority of the information actually recorded in the notes, about 80%. So you see there are 80% of the information was not utilized in a huge amount of study. And for those who used in the study, not to our surprise, but just keep emphasize here. This is showing you what kind of approach people are using. Some are using rule-based. Some are hybrid and statistics and unspecified. And their majority of them are actually using rule-based approach for their study. And from 2019 to 2021, to our surprise, actually, not much measurement study published. A lot of study are, actual use cases of keywords related things retrieved from the notes. So we see upward trend in the published observational study, but majority of them using rule-based approach. And there is adoption gap related to what happened to those advanced, border-based model, and what happened to all those statistical approach, why no one adopted. Then the things to our surprise, when we check the reporting, so those observational study, they say they use NLP methods. We see 10% of the study did not say what NLP methods they are using. 50-80% of the study didn't report what actually they mean about NLP. So they didn't define the model definition. 74% didn't report if they use standardization. 50-80% of the study didn't report in what kind of situation, the context they're using. So only 12% of the studies reported all three definitions. So you clearly see the translational gap. And the hypothesis is basically that, even we did a very cool NLP research, but that does not translate to how people being used. I don't want to illustrate more, but just showing you the gap we notified is that their moderate poor reporting of the people who use NLP for their clinical research. So now come to the digital era, move to the generative AI era. So we noticed the translation barrier. We noticed what we did successfully in one single institution does not truly translate to, enable many multi-sites contribute to other institutions' work. So come to this kind of generative AI help us to solve that problem. Specifically, this is the picture is that it is okay for us simply leveraging all the big data we have and come up with a solution to be directly delivered to end users, including clinical researchers and clinicians. Is this what we are aiming to go with the foundation models, where the knowledge to be put in the foundation models through large language model, where the data to be put into multimodality AI model, how do we go from this and to the wisdom component? Are we fine with that? Then translate to, how do we really think about the natural language processing? And the natural language processing, over the years, we've been progressed as an engineering problem rather than an AI problem. So you see all those different tasks we've been tackled as a researcher. And meanwhile, we see large language models is powerful as it transforms big data into something computational accessible for all other information knowledge management tasks. For me, I see a great utilization of that technology for this kind of effort, which we try to help recognize patterns, try to discover new knowledge, and try to make the big data consumable for things. But this is actually not truly new. Distributional semantics, so language models, this has been around for a while. But before the deep learning era, those things are, we couldn't do much with the data due to resource constraints. I still remember during my PhD study, I tried to do run clustering algorithms for 6,000, not documents, sentences. I don't have that memory to run those, to compare to building language models. Anyway, just jump through. We think LLM help us from text search towards semantic search. But we based on our dear friend Bill Hirsch, from OHSU, we still think search still need to be there due to healthcare settings, which is a high stack. We cannot deal with the generative component with some problems. We still need to have authoritative and timeless and contextual information needed for perform clinical task. Meanwhile, we do see, we probably have a possibility to transform the historical situation with low productivity to high productivity using generative AI technology. This is our recent exploration, which my team member tried to say, okay, few shot learning and RAG, all those couldn't solve token level task. But my advice to my team member is say, why you do token level task, not go to discourse level. And there are many things historically we have challenges to do. We may be able to speed up and to do that. And anyway, this is the one which is something we think about it is that this just published in Nature Medicine, which is to talk about instead of using proprietary kind of foundational models, if you use all the open data available in the public space, you still can do very well. And so in this specific article, we use all the public available text data, image data, and we'll be able to build a foundation model and achieving state-of-the-art performance for 16 out of the 26 clinical significant tasks. So comparable to GPT-4 model. The reason is basically is that if the data available in the public domain, especially those available through scientific domain, those data are generally very high quality. Because of that high quality, even the model is small, but they still do very well in those tasks. what I have. This one is a kind of just illustrating. I'm supposed to be an NLP researchers. I have no doubt on the great potential. However, the current business model it make us difficult for as academic researchers. And it capture data that are accessible. And so it's very critical, and they may there's some significant issue and thinking around it, but this should be the way forward. And this is what my team is currently working, is how do we use generative AI and a large language model to accelerate the development of small models. So lastly, that's the translational AI framework. We focus on things which are, any technology, we spend time on it, we hopefully that can have real world impact. So the framework I'm pushing and pitching up around it is this translational AI framework. I already illustrated through the OHNLP side. We want the structure to be team science. As a translational scientist, we should think about methodology innovations to address a problem, real world problem, not something we imagine that. We should take a team science approach, leveraging teamwork, and try to do the things innovatively, and try to do that better and with some sustainability model. We should also focus on translational science, as I illustrated. If the thing's not reproducible, not implementable, not transparent and explainable, we may hiddenly be a barrier for translation. And lastly, of course, need to be on the fair principles, which is make sure the evidence can be available and accessible, interpretable, and reusable. Where this is the real world situation, and any data we generate from the real world, including EHR data, including publications, literatures, there are significant bias in there. And ongoing research we notice a lot of publications, such as case reports, does not have any of the, basically does not have any, did very poorly with capturing the social determinant of health information in clinical research. And all those translate to something with our current data is lack of representation and is bias. And that gives us the things is that if we develop methods, develop models, on top of it, we may face the application injustice, the digital divide problem. And so go to my next slide, was the link back to the evidence-based medicine. This is what I firmly believe is that real world data actually give us a lot of opportunity to help us to design better study, come up with better evidence to move forward. And this is basically all the data we have can, because of the capability, be able to computationally access such a data through the technology, generative AI technology. We should be able to, come up with real world evidence faster, but at the same time, we should also take a, cautious approach, leveraging programmatic trials, leveraging rigor clinical trials to help us generate the evidence. We don't think, for me, I don't really think healthcare for the tomorrow will abandon the evidence-based medicine approach. You still needed to have the process to get the evidence and to deliver into the point of care. This should include predictive models and AI models. We tend to think they can be used directly. I'm very cautious about that because I noticed the significant difference of the data in a top 1 hospital and the data in the largest healthcare medical centers, how different they look. And I'm not going to say we can use a model built with high quality data, comprehensive data at Mayo to be deployed at, you know, my current institution, which is going to be not safe. I think that's the last slides. Oh my God, I take too much time, and I'll stop here and give we have minutes for questions.
All right. Thank you so much, Professor Liu. First, a big applause. In an amazing, perspective of a whole of career approach to using, information technology to sort of tackle this learning health system perspective. And I love the integration between these two seemingly different perspectives of evidence-based medicine and the data science perspective. So I think that's my favorite take-home message from this talk. And let's open up for questions. I have many, but we have a few minutes, so let's open up questions for the audience.